Nice. All right, Gina. All right, so I'll put here to get us started. If anybody's kind of scanning. So chapter 29, number 58. And I guess now I got to go back and read the question here. It says a uniform magnetic field of 0.15 Tesla is directed along the x-axis. Okay. A positron, okay, having a 5 times 10 to the 6th meters per second, moving at that speed, enters the field along the direction that makes an angle, at 85 degrees with the x-axis. And so they got a nice little picture there. The motion of the particle is expected to be a helix as described in section 2. Calculate the pitch P and the radius. Okay, so I was wondering how I might do something right-hand rule, but maybe you can see it here with the camera. If we have the x-axis this way, and I'm going to go ahead and put the y-axis in the plane of my paper. And then, so I'm going to leave it out. Well, maybe I'll try to draw it. This would then be the z-axis kind of coming out. But in the plane of the paper, what they're saying here is there would be a velocity vector. They give us a number of 5 times 10 to the 6th meters per second. They give us an angle of 85 degrees, and I believe it's from the x-axis. And my picture sort of looks that way. Let me see if I can hit the magnifying glass and zoom in a little better here, or expand it. Yeah, that's 85 degrees, and it's from the x-axis. So what we could do is we could think of this velocity. Maybe I should put in green here the magnetic field along the x-axis. But the motion of this thing can be thought of as a little bit in the y direction, and at the same time, a little bit in the x direction. And the reason that's important here is because the force, which is the cross product, says that the force must be perpendicular to both V and B. Or another way of saying the same thing is that only the velocity that is perpendicular to B is relevant. And so B is along the x-axis, and so this is the relevant piece. You see it in the math when you say, okay, the magnitude of it is QVB times the sine of the angle between them. And so in this case, the 85 degrees is the angle between the B and the velocity vector. And so this V and, well, maybe I'll write another step, but this V sine of 85 degrees is the velocity in the y direction. Now, I don't know if that's such a big deal because we could calculate it, but here's what you would get then. If you wanted to know its direction, you would, of course, take the V and put your fingers in the direction of V and close your hand towards B. And so that's the direction of the V cross B. So immediately the force is in the negative Z direction, which is why it's going to kind of corkscrew like this. It's going to get pushed, and I don't know if my picture can draw as nice as the one in the book there, but it's going to corkscrew along here. Which way it corkscrews, clockwise or counterclockwise, probably really isn't important. But what is important, though, is really kind of figuring out, well, that's the question, what is the pitch? But I'll start with maybe with what the radius is, because here's where we got to put together this semester with last semester. This would be the force, and that would have to equal to m v squared over r. And again, maybe something that's not quite so obvious here is which v is it. And so again, it's the velocity, the part that is making the circle. And so this is the y component again. I guess what I'm trying to say is you could look at the motion of this corkscrew in two different pieces. A velocity that is, and sometimes we'll put this perpendicular to the B field, and a velocity that is parallel to the B field. Now the B field is along the x-axis. So to make maybe our discussion a little easier, they were nice to give us the B field along the x-axis. So I would want to look at this problem, okay, is the velocity that is perpendicular, that's the part that's going to make a corkscrew, and the part, or the circular part of the corkscrew. And the part that is parallel would have no force on it. This is the part that's going to then be continuously moving down the x-axis. And so that's what would determine the pitch of the corkscrew. That is the distance p between one loop and that, the start of the next loop. And so that's the pitch.
Dr. Young, I'm sorry to interrupt you.
Oh, please do.
Okay. I didn't understand why, if it was entering the field at that 85 degrees, how come it remains along the x-axis once it enters the magnetic field? Why doesn't it continue its trajectory up and to the right?
Oh, okay. Well, with no forces, okay, an object would go in a straight line. But this does have a force. This is this magnetic force, V cross B. And so maybe I'll draw a difference picture here for a second. Let's say, for the sake of discussion, and even face-to-face, this is kind of hard to see. I'll try to do my best here on a camera. We like to use a green color, so I'm hoping this green pen helps. But let me make a magnetic field that is coming towards, the screen here. And so you can put a little dot here. It would be like if I were to hold this pen pointing at you on the screen. That's the direction of the field, pointing right at you. Okay. And if you have something moving, and in this case, they said it's a positron. So I'll make it a P plus here, and I'll say it's moving this way. The main point of this chapter is that a moving charge in a magnetic field will have a force on it. And this is the equation for that force. And so in section 2, they're saying if this is the force on a moving charge, what would it do? What would it look like? What kind of response would it have? See, because if there was no force, it would just keep going in a straight line. And I kind of got the impression that's what you were saying. You were saying, well, wait, shouldn't it enters here. What's to keep it from going in a straight line? And of course, the answer is, well, no forces would mean it goes in a straight line. But we do have a force. A charge that's moving in a magnetic field will have this force on it. And so if I can kind of summarize section 2, I keep saying section 2, no, I'm questioning that. I think it is. But early in the chapter 29, they're saying this is the force on an object in a magnetic field. So my question then would be, okay, excuse me, if this is the force, what does it do? What kind of pattern does it have? And I think the best way to see that is to start off by saying, well, what if we just take a simple case being the motion of the charge is perpendicular to the magnetic field, because the V cross B tells you the direction of the force. So that's where this little trick with our right hand comes into play. You put your fingers in the direction of the first vector, which in my picture, it's going to be hard for me to get my right hand on over here, but it would look like that. And so that would be the direction my fingers of my right hand are pointing in the direction it's moving. Then also adjust your right hand so you can close your fingers towards the second vector, B. So I can put my hand here, and then maybe I twist it. I'm going to have to stand up here this way. Okay. So my fingers are in the direction of the positron, and my fingers can now close upward, which is the direction of the field. And then the thumb gives me the direction of the force. And let me call it the initial force. And so what this is saying is if you go V cross B, the force is downward. But here's what makes this kind of a hard idea to understand is once the object gets bent downward, then its direction, its velocity direction changes, which means then the direction of the force is going to change. So just for the sake of discussion, let me have it bend so that it goes all the way straight down. And if you do the same kind of thing here, you put your direction in the velocity it's moving, so my fingers are going down. My palm is up so I can close my hand towards the direction of the magnetic field. My thumb then is the direction of the force. So now this would be the direction of the force. So initially the force was down in my drawing. Now it's to the left in my drawing. And so it would bend it like this. And then when it gets here, it would be V cross B and the force would be up. And so I didn't do it at every location along this circle, but the point I hope am I getting across is that if you always have a force that is perpendicular to a motion, going back to physics 121, that would mean that force always changes its direction. It does not change its speed. It does not make it go faster or slower. So we like to say magnetic fields do not add or take away any kinetic energy from the particles. It does not make them go faster or slower, but it does turn them. And in this case, we would have a circle. Now, if we extend that one step to this problem and say, all right, what if, going back to here, the positron is moving not perpendicular to the field, because that would be the y component, but in this case, it has a velocity that most of it is perpendicular to the field. That's the y component. But some of it is still moving in the x direction. Well, here's what we do. We look at the velocity as its two pieces. We look at the part that is perpendicular. And so the part that is perpendicular, this would be the y component. And that would look like what I just tried to describe here. The part that is moving perpendicular would go in a circle. Then there would be the additional piece that would be parallel to the field. So in this case, it would be the velocity in the x direction. Well, what would that do? Well, according to the right-hand rule here, right? I guess here, the part that's parallel, the angle would be 0 degrees. And so 0 degrees would mean 0 force. And so the part that is parallel to the field, the x component, really does not have a force on it. So it just keeps doing the same thing. And so my question for you, and kind of a conceptual one, I guess, here is, what is a circle and at the same time a circle around, going around the magnetic field? So this is what I mean by a circle. This is my circle going around the flux of the magnetic field, plus a motion along the magnetic field. Well, that's where a corkscrew comes into play. And so this would be going around in a circle because of the y component of the velocity. So this is the part that makes the circle. And then this is the part that just continues to move. This is the part that would have no force on it. This is, Newton's first law, that if you don't put a force on it, it just keeps going in the same direction. So the part that is in the x direction just continues on. And so I would have this circle. So if I can, have my circle and then a motion this way, I get a corkscrew. It's a circle, and each little circle moves a little bit along on the x-axis. Did that help at all?
It did. And I hate to ask you this again, but can you do the right-hand rule and demonstrate how it forms a circle for 58?
Okay. All right. Now, again, let me emphasize that I'm going to look not at the total velocity, but at the velocity part that is perpendicular. Okay. So just this part, the y component. And so my cross product is saying this. Put your fingers in the direction it's moving. Okay. So originally, just looking at the y component, my fingers would go up. The magnetic fields would be in the x direction. So I'd kind of twist my right hand like this. My fingers are going in the direction of V. I can close my fingers towards X. And my thumb is pointing. You can't really see my thumb because it's pointing down, but my thumb is pointing in to the paper. So the initial push would be to push it into the negative x-axis. And so I'll just kind of redraw this. So this is the original velocity, so Vy. This is the magnetic field. The push would be perpendicular to the velocity. Perpendicular to the velocity turns it. So it's going to turn into the paper. And of course, once it does that, it is now moving in the negative z direction. And so if we go through the right-hand rule, the negative z direction would be into the paper. I guess I'd have to kind of hold my hand this way. And I would then close it. And it's kind of hard to see. I'll turn it over, but this is my fingers pointing in the positive z direction, closing towards x. I want to turn that over and have my fingers starting in the negative z direction and closing. I'm going to close it towards x. right here, closed towards X, now my thumb would be pointing down, and so the force would be this way. And so we end up getting a circle where the velocity keeps going from a y direction, then to a negative z direction, then to a negative y direction, then to a positive z direction, then to a y direction, and it just makes a circle around the B field. I'm wondering if I were to grab a picture and use my screen differently. Let me stop sharing here. Let me go to the textbook. I think there's a good picture of this in section 2 here. Oh, there's a couple pictures. Let me start with this one. Let me see if I can grab this picture. Okay, got it. And let me go to my whiteboard. No, that's not what I wanted. Whiteboard, there it is. Must have closed it this morning. And let me go paste. Ah, nice. And then I'll share that with you here in a second. Okay, so that looks really good. All right, let me go back to Zoom here. Let me go to share screen. Let me grab my computer marker. Okay, so I'm gonna try this again here, Gina, that if we take this one down at the bottom as the one that's originally moving, the V is in the x-axis here. And the magnetic field is into the paper. So the right-hand rule would say V cross B makes a magnetic, a force. Yeah, magnetic force, what I want to say, is this upward one right here. And so that's why originally when this comes in, it's going to get deflected upward. But somewhere else along its path, the force will be in a different direction. Because remember, the force is always perpendicular to the velocity vector. That's what a cross product means. And so everywhere along the path of this positive charge, the force would be perpendicular to its motion. And so this is where the part that I say you got to go back to physics 121 for. A force that is perpendicular changes its direction. Just like a force that's in the direction it's moving makes it go faster, a force that is in the opposite of the direction it's moving makes it go slower, and a force that is perpendicular turns it. And so this thing would sit here and turn and go in a circle. And that's what the perpendicular component looks like. And in fact, if I jump back to the textbook and go up a page, I believe, or is it down a page? Maybe it's down. Your author has a good picture of somebody with their right hand, and I don't see it at the moment. Let me try that again. Let me go page up. Don't see it, don't see it, don't see it there. Where? Ah, there's the the author's little right-hand rule here. Let's see if I can copy this one and bring it over to the Zoom meeting here. So copy that. Let's come back to the whiteboard here. Let me write below it here, do a paste. And so here's what the author's trying to say here is take this right hand and put your fingers first in the direction of the velocity. So maybe if you can kind of picture this right hand, I don't know, maybe right there somewhere. The fingers would be pointing in the direction of the red right here. So here's the fingers. And then the palm would have to be facing inward. So palm would go in. And then that would make your thumb right here. And if you do that anywhere in here, you're going to get a force that is always perpendicular. And a force that is always perpendicular is a force that makes a circle. Now, that's just the part that's perpendicular. Let me kind of grab another picture out of your book here, see if this one helps. Because the simple case is when it's moving perpendicular. This picture here, I think, is an exact copy, really, of what's going on in this problem. It's the more general case. It's the helix. Let me see if I can paste this one in here. Let's see. I'll put this right here. Here's what your author says is, the helix pattern. And says, if you start right in, say, this area right here, with the velocity going up, there's the velocity, and that's the direction your fingers would point, then your palm, so maybe I'll put finger, then the B field is the direction of your palm. And so that means your thumb, which is the direction of the force, would be in the negative Z direction. That's exactly what this problem is. But once the object moves to, maybe I'll just change colors, up here near the top, now the velocity is in the negative Z direction. So that would be the direction of your fingers. Now your palm would still go in the direction of the field. But if you do that, or maybe you picture this right hand over here, you're going to get a force that is downward at that point. And so the tricky part about this is to realize that the force keeps changing its direction, because the force always has to be perpendicular to the velocity. So if the particle changes its direction, so does the force. The good thing about it, though, is the direction of the force will always be perpendicular to the velocity. And that means it's always changing its direction, and it's always changing it at the same rate. And that is the definition of a circle. The definition of a circle is change your direction always at the same rate, always at the same rate. And so the point of section 2 is to realize that the velocity that is perpendicular to the field will make a circle, and the part of the velocity that is with the field, and in this case the x direction, it just keeps going along that x direction. There is nothing that changes, and so that makes this spiral pattern, this helix pattern. Did that help?
Starting to click for me a little bit better. Thank you.
Okay. Okay. So with that in mind, I'll let it keep sinking in and clicking a little better. Let me go back to my camera here, and then we can put in some numbers. But yes, that visually is tough, and an important step to realize that we're going to get a helix, and not just a helix itself, but the fact that the velocity that is perpendicular to the field is the part that makes the circle, and the part of the velocity that is with the field is the part that moves it along, that's going to give it this kind of this corkscrew, or what your author said is going to give it the pitch. And so I would, I guess, coming back to maybe a clean sheet here, or at least as clean as I got. Got to put a piece under there. But what I was trying to say here then is, if I tried to draw this so that this is the x-axis with the magnetic field along the x-axis, and this the y-axis, and with the initial velocity here, there would be a y component that's going to be going in a circle, and then there would be the x component that would have no force on it, and it would just keep going along in the x-axis. And so you're going to get this corkscrew effect. The best word is a helix. And so coming over to here, saying that the magnetic force then would be Q V cross B, then we can just write the magnitude of it as Q times the velocity in the y direction times B. And like I said, that what we just talked about for the last, I don't know, 10, 15 minutes is probably the toughest part of this problem, is to recognizing that it's going to be a helix. But once you recognize that, of course, you also have to recognize the velocity that is perpendicular to the field. So that's the y component, is the part that makes the helix. This would have to equal to mv squared over r. And of course, this would be the y component also. So this mv squared over r is what I'm taking out of your Physics 121 class, objects going in a circle. And I'm just setting that an object going in a circle has to have a force on it. So I'm taking what we're learning in this chapter, which is the magnetic force, and setting it into the centripetal force. Now, of course, a hard part of that is to realize that the velocities they're talking about is not the total velocity. It's only the y component. Of course, then this can cancel off. And I think this was one of the questions. Oops. Solve for R, Q, and B. And so let me come back to the problem now. It said calculate A, the pitch P, and B, the radius. So I guess I'm actually solving for B first. And so now I can put in my numbers. So they call it a positron. You may not be familiar with a positron, so let me just point out a positron was kind of a surprise discovery in 1930, I think. But science were doing some experiments and discovered that the electron kind of has a twin. It doesn't hang around long, so we've never noticed it. It doesn't occur naturally in nature, or if it did at the beginning, at some point in the universe, it's all been annihilated and swallowed up. So we don't have any locally around us. but our experiments were just humming along, and nobody even thought about it, predicted it. They just showed up, and it was like, whoa, what's this? But a positron is just like an electron, except it has a positive charge, and it's also made out of something we call antimatter. We call it antimatter because we don't really know what it is. We just know that when you take it and put it next to matter, they annihilate each other. So if you take a positron, you put it next to an electron, they convert into energy, big flash of light, a lot of electromagnetic energy, but when it's all said and done, there's no more electron and there's no more positron. So that's the biggest difference, is it's made out of this stuff called antimatter, which again is why we know we don't have any antimatter around, because it reacts with matter and kind of magically disappears. So, and a big explosion at that. So we kind of think that maybe there is some, or was some antimatter at the beginning of the universe, but not anymore. But the point is, in this calculation, I can just put the mass of the electron. So there's the mass of the electron.
No, your teeth is a part of your health. It is. I'm not.
Did I hear a question or no? All right. So now the other thing to do is to get the velocity in the y direction. Now the velocity total, they said, is 5 times 10 to the 6th. So if I multiply it by cosine of 85, I get the y component. And again, the charge is just like the electron, except it's positive. I'll put the 1.602 times 10 to the minus 19, and the magnetic field is the 0.15. So, grabbing a calculator here, I have the 9.11 times 10 to the negative 31 times 5 times 10 to the 6th times cosine of 85. I'll divide that by 1.602 times 10 to the negative 19. I'll divide that by 0.15. And so this has a pretty small radius, 1.65 times 10 to the negative 5 meters. And just out of my own curiosity, before I get to the other half of this, part A, let me call up the solutions for this chapter and scroll down. What did we say? 58. And see what they got. Oh, wait a minute. They got a little different number. They got the same formula. Oh, shoot. My bad. Looking at the wrong picture. This would be sine of 85, right? I mean, this is the 85. And for some reason, when we got sidetracked and started talking about the corkscrew, I was thinking this was the 85. Anyway, so we want the sine. So yeah, that's why I got the wrong number. Okay, so let me try that again. Let me go re-enter, and I will just arrow back here. And oh, what if I go sine 85? Yeah, nice. Okay. And 1.89 times 10 to the minus 4 meters. All right, now let me check that with the answer. Yeah, okay, so the book and I agree there. All right, so I actually think that's the easier part of this one. But the part A then is to say, now, what was its pitch? Now, the definition of the pitch, if you're you're not familiar, is this little p. It's how far is it from one loop to the next.
Physics.
And I'm just going to use, going back to physics 121, this little equation, that if there's no acceleration in the x direction, and so there's not, remember, there's no force in the x direction. That was our argument here about the magnetic field, that the magnetic field applies a force that is perpendicular to the field, but never in the direction of the field. So there is no force in the x direction. And that's why we said whatever velocity it has in its x direction, it just keeps going. So this would be the v, and here's where I want cosine of 85. Now, I still need the time. So here's where I got to come back really to this problem and say, all right, how much time elapses as this positron makes a corkscrew? And so if you just think about it as a circle, you might say distance equals velocity times time. So I'll say it again. It's maybe a little bit hard to digest, but the magnetic field does not make it go any faster. And so as it goes around in a circle, it's keeping its same speed. And this is the radius. And so if you think about this as the velocity, I'll call it the y direction, but it's also the z direction later on, then it's the y direction, then it's the z direction, then it's the y direction, then it's the z direction as it goes around in a circle. And the distance it would travel would be the circumference of the circle. So this would be 2 pi, where the radius is the 1.89 times 10 to the negative 4. And the velocity of it doesn't change. So I might as well take that initial velocity in the y direction. That's 5 times 10 to the 6 times the sine of 85, and then multiplied by t. So this is how I'm going to get the time that I'll use to figure out what the pitch is here. Okay, so I've already got the radius in my calculator, so let's go times, and then times a pi, and then times a 2, and go enter. So that's the circumference of the circle it goes under. So if I divide it by the speed, which would be 5 times 10 to the 8th, and also sine of 85 degrees, this should be the time for one revolution. Wonder if your author calculates that. No, he doesn't calculate the time. He gives a little formula for it, but he doesn't give a number. So assuming that's correct, I'm going to take that time and put it right here, and then multiply it by the velocity in the x direction. So times 5 times 10 to the 6th multiplied by cosine of 85. And I get 1.04 times 10 to the minus 4 meters. And he got, I'll do it the same thing. So there's the pitch, how far it would go. All right. Well, Gina, I'll let you let that one sink in for a little bit. But yeah, I didn't realize how important this one was to really understand the helix pattern and why the helix, not only why it's a helix, but then what velocities to use. And so we need to look at the perpendicular velocities to the field as well as the parallel velocities of the field. So in this case, the parallel is the x component and the perpendicular is the y component. And keep those straight. And I'll say it again, the y component is the part that goes in a circle. And then the x component is the part that moves along the x axis.
Are you able to explain one more time how there's no force in the x direction? If it comes in at an angle, shouldn't there be an x and a y component? How come we can disregard the x component?
The x component of the velocity is unimportant because, how do I say this without getting too mathy? I don't know if I can. This is the equation for the force. And if you study a cross product well, so if this is the v vector, and then this is the b vector. The meaning of this cross product is q v b sine theta. And the whole reason this math was invented is because right here, this if you put this v and this sine theta together, so if the angle between them is theta, then this right here, the part of the velocity that is perpendicular. So if I take, I'll change colors here. If I take this velocity vector in green, and I break it into a piece that is in the same direction as the magnetic field, parallel, and a piece that is perpendicular. The part that's perpendicular would be v sine theta. This is it right here. The only part that comes into play is the velocity that's perpendicular. The part that is in the same direction of the magnetic field does not deflect it. And that's why this math was actually invented. I mean, my simple answer is that this is what a cross product means. It means do not consider the amount of the vector that is parallel to the first one, just like a dot product. A dot B meant how much of vector A is parallel to B, whereas A cross B means how much of A is perpendicular to B. And so that's why we have these two vector multiplications, is because sometimes the physics wants us to pay attention to how much are in the same direction. And we saw that when we did work. We had work is F dot dr. We didn't want to use the whole force. We only wanted to use the force that was in the same direction as R. Then we did cross products back when you learned about torques. We said torque was R cross F. And the reason we did it that way is because when you have, say, a bolt and you put a wrench on it, if you grab the wrench and you push, say, well, most people would push perpendicular, as you should, but maybe because some other component in your engine is blocking your hand, so you have to push in a direction that is not perpendicular to the lever arm. The only part that is relevant to rotate the wrench is the part of the force that is perpendicular. The part of the force that is parallel doesn't turn the bolt. It just pushes on the bolt. And I guess if you push really hard, you'll break the bolt off. But none of this force is relevant. So that's why we write it as a cross product. The cross product is the mathematical technique that you learned, I guess, in Physics 121 first, and you're seeing it again now, and maybe even saw it in a math class, that allows us to only care about the part that's perpendicular. And it's because of that sign. And it's also, we have this math because of nature. You know, nature, something like this wrench, Nature says the only part we care about is the part that's perpendicular. Now, when it comes to the motion of charges in a magnetic field, the early scientists noticed that when the electron or positron went in the direction of the field, there was no force. It's only when it moved perpendicular. So they knew that the equation for the force had to have a cross product in it. It had to be V cross B. It was only relevant for the part of the velocity that was perpendicular to the magnetic field. So if you ever see cross products, that's what they're telling you. Cross products is saying, look at the parts of the two vectors that are perpendicular to each other. Or if you see a dot product, they're telling you only look at the parts that are parallel to each other.
So for 58, because the magnetic field happens to be only X,
Yeah.
care about the Vy.
Right. So when it comes to the circular part, I care only about Vy. When it comes to the X part, that is the pitch, I care only about Vx.
Okay.
So the absolute critical thing that I got to get across here is that you got to take the motion of your charged particle and break it into the two relevant pieces, the part that makes the circle and the part that makes the pitch.
Okay. Thank you, Dr. Young.
Good. All right. Now, let me jump back here to the chat room. I know before the break, Scott, we had left you with a question. I hope you were able to jump in here. Let's see.
Yes, I'm here.
Good. Oh, and I don't see anybody throwing anything into the chat room yet. So I'm going to go with you, Scott, just because I knew you have been waiting here for a while and we ran short in the last break. What was your question?
I believe it was 35. Yes, 35 on chapter 29.
All right, let me clean up a little bit here, my desk. Number 35. Oh, I'm sorry, I missed you. Chapter what? 28?
Chapter 29.
29. Oh, yeah. Yeah. Okay, and then it looks like I got to the end of my pad of paper. Let me grab a new pad here. And I'll even get a new clean sheet to tuck underneath it. Hopefully I can keep it clean when I go to the next page. All right, and let me just write down a time so I can kind of get a rough estimate of the timestamp here. 1:26, okay, page 1. And if anybody's kind of scanning the video, I'm going to put here chapter 29, number 35. Good. All right, and then for me, I need to come and read it. You guys really, I know that in theory, everybody would be working with chapter 29 all week long, but I think in practice, not too many people have gotten too deep into 29 yet, because most of my questions this week have been 28. I haven't even got a chance to read much of these questions. Anyways, but now I am. So let me get to the question, scroll back here to 35. Oh, yes. I can see a little torque coming here again. And actually, I'll use this as a chance to point out that one of I think the challenge, and this might have been the challenge on the last problem too, is incorporating last semester with this semester. Because we got, the last problem I just did had that centripetal force and that cross product stuff. And your author doesn't spend much time on that in this chapter because in theory, you learned it. But I know in practice, that was either a semester or a year ago. So in one sense, I think this is a good chapter. It forces people to go back. Anyways, I believe this is a torque one. Just looking at the picture, I'm trying to remember when last time I would have read it would have been last year. But it says a rectangular coil consists of n equal to 100 closely wrapped turns and has a dimension of A of 0.4 meters and B 0.3 meters. The coil is hinged along the y-axis and its plane, this is important here, plane, yeah. makes an angle of 30 degrees. Oh, also I should point out, the other thing that makes this chapter a little challenging is not just remembering the Physics 121 stuff, but it's trying to get a good picture in 3 dimensions of all this stuff going on. And so I'll try to redraw this in 3 dimensions because they've got an X, Y, and a Z. And it's important to know what the 30 degrees is, as well as what is the dimension A and B. But the picture does a pretty good job of that, but sometimes you got to look at the picture for a couple minutes to really comprehend what they're after. Anyways, but it clearly says the plane is at an angle of 30 degrees to the x-axis. What is the magnitude of the torque? Now I'll pause there. Notice they didn't say direction, although I can do direction too, but it says magnitude of the torque exerted on the coil by a uniform magnetic field of 0.8 Teslas, but is directed along the x-axis. All right. So the picture the author has a grid, and the grid has kind of the traditional X to the right, Y going up, and Z coming out of the paper, although kind of hard to visualize. I'll draw it like that with maybe a negative Z going in. And then it takes this rectangle. Now, I'll kind of try to see how it shows up here on the camera, but if I let my sticky pad here, my Post-it notes, be this rectangle, they're saying there's the x-axis. Here is the y-axis. The rectangle has a hinge along the y-axis, and it is flipped up here 30 degrees. Okay, so maybe in a different color, I'll try to draw the plane of the rectangle with a 30 degrees coming off the paper. Maybe I shouldn't use yellow on yellow. What if I grab this notepad and put a white here? It's saying pivot it up 30 degrees. Okay. All right. Well, you're shaking your head like you kind of get the picture. Okay. Now, the one thing I think would have helped in this problem is the direction of the magnetic field. So I'll get my green pen, since your author likes to do magnetic fields in green, or at least the survey book likes to do them in green. So there's the magnetic field. But definitely remember the magnetic field is there. And so I'm going to go to this equation for torque. The torque was the number of loops times the magnetic moment crossed with the direction of the magnetic field. Okay, so there's a cross product there. Okay. Now, he works this out, and you're shaking your head like you've seen this, so I'll keep going. This right here is the current times the area vector. Okay. Again, you're shaking your head like, okay, I get that. All right. So let me put in my numbers. And I am going to just do the magnitude of the torque. So it would be an N times an I and an A, because that's what the magnetic moment is, times the B times the sine of the angle between those two vectors. And so this kind of goes to our conversation I was having with Gina a few moments ago, that this is a cross product, okay? And there's many ways to do a cross product, but like last problem and this problem, our focus was on the magnitude, and this is, I think, if you're just after magnitude and you've got a picture so you can deal with angles, this is the way to go. All right, so now I can start punching these things in. They say that it's got 100 different loops. Okay. They say the currents, did I read here? What is the magnitude of torque exerted on the coil in a uniform magnetic field of point A direct along the x-axis when the current is 1.2 amps in the direction shown? Okay, so I'll worry about direction here in just a second. What is the expected direction of the rotation? So the expected direction of rotation would be the direction of the torque. So I'll start with the easy one, just what is the magnitude of it? So the area, well, that's pretty easy. That's the 0.4 times the 0.3. That's the dimensions of this rectangle. Okay, so there's the current, there's the area. This is the strength of the magnetic field. That's the 0.8. And I think the challenging one of this, and you didn't really say, but I'm guessing is this angle.
Yeah, this is the part that I'm failing to see and why it rotates. Well, I'll wait for that part, but this is one of the parts I'm having issues seeing.
Okay, so let me come back up to my drawing, and let me do a cross section of the x-axis and the z-axis. So this would be like taking this, and so if I had this rectangle, or I guess this dimension is bigger. So if I had this rectangle and it was pivoted upward, it would be like, and remember this with the y-axis going this way.
Mm-hmm.
So if you imagine me kind of taking a chop here and looking down from above, I would see this rectangle angled out at 30 degrees. And remember, this is the direction of the magnetic field. So the magnetic field is in the x direction. The definition of the direction of the area vector, like we did for electronics, or I should say electric fields, is perpendicular to the surface. So in this cross section, perpendicular would be, and I'll go in both directions like that.
Oh no, it froze.
No.
Darn it.
Okay, that's okay. I'm gonna share it again. Had the thing free a couple times today now.
I've been having Wi-Fi problems in my house too, so it's not just you, Dr. Young.
Oh, good. Yes, this.
I even upgraded our internet to the panoramic Wi-Fi, and every once in a while it just decides it doesn't want to work. Okay, I can see now.
Okay, yeah. So what I drew when it froze, I'll get a different color here, but I was drawing this line that is perpendicular. Probably doesn't stand out real well on the yellow paper. But
I can still read it.
okay, good. But now, so what that would mean, and I'm sorry, there's one more step. It's perpendicular. So is it pointing this way, kind of down towards the z-axis, or is it pointing away from the z-axis? And the answer to that is it depends which way the current is. And so we take our right hand and we hold our fingers in the direction of the current, and then our thumb will give us that direction. So if I come back over to my original picture that's supposed to be 3 dimensions, I'll see that this top piece has the current coming out away from the y-axis, then going down this leg of the rectangle, then the part that would be in the XZ plane would be going in, and the part of the rectangle that is on the y-axis is going up. So if I use my right hand in this picture, curling it this way and pointing towards the z-axis would be wrong. I would want to hold my right hand so my fingers curl with the current. So these are my fingers here. This part of my finger is going up, and this part of my finger is going across the top. And if I make it real tight, this part of my finger goes down. So this right here, coming back to this picture, is the area vector. Okay.
Okay.
Now, actually, here's some good news. The sine of either one of these is the same number, since the sine function is a supplemental angle. One's going to be a little under 90 degrees. The other one's going to be a little over 90 degrees. So I guess what I'm saying is we don't have to make a distinction between whether it is pointing this way or this way in order to do that calculation. However, they do ask for the direction of the torque, and so since that has to do with the direction of the area vector, I'm eventually going to need to know what is the direction of the area vector. So,
How did you know to, I guess, I mean, I'm following that you curled your fingers in the direction of the current, but what did you point your fingers in the direction of first to begin with?
When I say point, do not think straight line, think circle. See, I'm going to put a fist here. See my right hand? See my index finger?
Yeah.
My finger is pointed in a circle.
Okay.
I want those fingers to be the same circle or rectangle that has the current. So if I try to take just my index finger alone and I put this rectangle here, if I were to lay my index finger over this rectangle, I would say my index finger is pointing this way.
Which is the wrong direction.
Which is the wrong direction.
Okay.
I would want my index finger, ouch, like this. Like this. Maybe you can see it better with my pinky. I want my pinky like this.
So is this the cross product, the right hand rule again?
Oh, hold on. Yo, whoa, 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 whoa. That's a whole nother right hand rule. So let me make it clear. I've got 2 right hand rules going on here. I haven't even mentioned the cross product. I know I did a lot when I talked with Gina, and that's coming for the second part of this. And so I'm going to do the right-hand rule for vector cross products. This, you might say, is just the right-hand rule to try to figure out what direction the area vector is.
Okay, I
So
am following now. For some reason, I was thinking it was the cross product.
Right, I know. My bad, because we have many right-hand rules, and we get lazy and we just say the right-hand rule like there's only one of them.
Okay, I'm following now with this part then.
Okay, so when you do a cross product, I will be moving my fingers like this. And so that would be the right-hand rule for a cross product.
Okay.
When I'm doing this rule, and some more, just to scare you a little bit, some more right-hand rules that you'll see in the next chapter, a lot of times they're done by just making a fist.
Okay.
and you don't move anything in your fist. And the part I'm glad you pointed out, because I will try to remember that when I'm helping other people, is when I say what direction my finger is pointing, I really don't mean a straight direction. I really mean which way are my fingers coiled.
Okay.
So coming back to this rectangle, if this white piece of paper is supposed to represent that rectangle, I could hold my right hand this way and be perpendicular to it, or I can hold my right hand this way and be perpendicular.
Yeah. Okay.
And the direction I would want would be what I'm doing now, because as I look at my pinky is making a circle in the same direction that the current is going.
Okay.
All right. And so that might have been your biggest challenge on this, was realizing that there is another right-hand rule to get that direction of that area vector. All right. So in this one, that's how I got that this area vector is actually pointing back here. And it might be easier to see in this drawing, because if I extend it out, we're talking about that angle right there. That's the angle between the B and the area vector.
Okay.
And maybe just to translate this here, remember down here is 30 degrees, so that must be 60 degrees right there.
Okay.
So that's the big piece of this puzzle, is what angle to put there. And so the angle is 60 degrees.
So that part there, the sine of 60 degrees, it's, I guess you could use the right hand rule to figure out where you should be looking and how you should be looking at it. I think that's the other I'm just failing to see. So what would you point your fingers in the direction of first?
Oh, okay, I see where you're going. You're going to the second half of this. Okay, so I'm going to go there, but I want to put in a number here just for you and for anybody else who might watch the video later on. And also just to check the number, see if I'm doing things right. But here is 100 times 1.2 times 0.4 times 0.3 times 0.8. And then, of course, this was the main part of our problem, was what angle is it? And I get a torque of 9.98, and the units for torque are Newton meter. And so I'm going to jump over here to the solution, number 35. Let me scroll up. And 9.98, yeah, Newton meters. So I got the number right. And of course, now you're on to the second part of this question, which is what is the direction? And I'll use this as an opportunity to say it again. I think one of the hard things about this is we are doing torques, which was in 121. And so that was either a semester or 2 semesters ago. And it was one of the hardest things we did in 121. Okay, but here is your main idea, that I've got 2 vectors. The area vector, and so I'll just go the direction of the torque, would be N times this mu, which is the current times the area vector, cross B. All right, so if we just want to figure out what direction it is, we have to do a cross product between the area vector and the magnetic field vector. And so let me just repeat these cross products, which if you're doing the OpenStax book, you would have saw it in chapter 2. And I think you did, right? Did you were 121 last semester, did the OpenStax?
Yeah, I believe so.
Okay. Anyways, the cross product says this: to figure out the direction, hold your right hand, I'll hold it kind of flat. First, put your fingers in the direction of the first vector. So the problem I'm about to do, this would be the direction of the area vector.
Mm-hmm.
Then rotate your palm. So there's a lot of ways I can rotate my palm and still leave my fingers in the direction of the first vector. Okay. But let's just say for simplicity, the second vector B is coming up like this pin, coming, towards the video. So once you get your palm in the direction of the second one, which is another way of saying you're able to close your fingers towards the second one, your thumb gives you the results of that cross product.
Mm-hmm.
Okay. So in this case, I would want to put my fingers in the direction of the area vector. I would want to then rotate my wrist until my palm is in the direction of the magnetic field. And then my thumb is going to give me the direction. All right, so let's see if I can get my right hand. I'll get around behind my desk here. But if I can get my right hand with my fingers in the direction of the area vector, I got it. But now, sadly, at this point, as you can see, my palm or my fingers do not close towards the second vector, the magnetic field. So I need to rotate my palm, like that.
Okay.
So now I'm rotating towards B. And so that means the direction of the cross product is the negative y direction. So if I were to finish this problem and say, okay, the torque then would have a magnitude of 9.98 Newton meters, and its direction would be a negative j hat.
Okay.
Now, we still have one more step here. What does negative j hat mean? Well, that means if you have, say, the y-axis, so here's the y-axis, here's the x-axis, and again, we're going back to last semester when we did our rotational motion. When something rotates, when the mass rotates in this direction, and this is kind of like the current we just did. If you took your right hand closed in a fist, so your fingers are in the same direction that the mass is rotating, we would say it has an angular velocity or an angular momentum or an angular acceleration in the direction of your thumb. It's a y direction. So a negative y would mean it rotates this way.
Oh, okay.
You would take your right hand, make a fist,
Mm-hmm.
you would curl it so your fingers are curling around in the direction of the mass and pointing in the negative y direction. So this thing should rotate, if I came back to this picture, like that. It should move over towards the y, move away from the x-axis and rotate over to the z-axis. If I put this rectangle down here, it would say this. Once you pass current through here, it would go like that. That would be a negative. Okay. Like that. Yeah. So
Well, all right then.
Ah, that was a good one. A lot of cross products. Well, again, torques, cross products. And good, I'm glad you pointed out that. I need to emphasize that, those two different right-hand rules. But I'll say it again, I came across it. You did two in your 121 class, because you had not only the right-hand rule for the cross products, but you also had this right-hand rule for figuring out the direction of something, its angular momentum or its angular velocity, by just making a fist and using your fingers as the direction the mass goes. And so if it helps this semester, I'm really doing the same thing here. I'm just making a fist, and now my fingers are going to be the direction of the current. Because we have moving charges, we don't have moving mass. So we're not doing mechanics, but it's really kind of the same pattern and makes it easy to remember.
And is that the magnetic moment?
Yeah. And then we
Okay.
call that mu, the magnetic moment. So this equation starts off, it looks so easy. It's like, oh, look, I just got to calculate the torque.
It's a little deceptive.
But it's got a cross product in it, which got directions, and it's got a three-dimensional picture. And even the magnetic moment has two other factors in it, the current and the area.
Okay.
Oh, and I got a negative Y. I guess I should check the answer. Did the answer say negative Y?
You're correct.
Okay, good.
It said clockwise. It'll rotate in the clockwise direction, which means that the
Yeah, it's looked from above, a clockwise direction. Yeah, I see. Yeah. Okay, good. Yay.
okay. Thank you very much. Appreciate it.
Oh, good one. All right. Not bad.
Could you explain the negative J hat one more time?
Where it came, or what it means, or both?
Where it comes from when you did the right hand rule with your hand, where you were pointing.
Okay. Maybe I'll start with a clean piece of paper here. But the right hand rule is, and I told Scott it was in chapter 2 of the OpenStax, and I still think it is, but I'm not 100% sure. I know the Survey book kind of does the cross product a little bit later, because you don't really need cross products until you actually do torque, which is
I think you're right, though. I think we did it in like the very early chapters. We covered like scientific notation, and then we did vectors, and we covered it very early on, and then we kind of just forgot it until we got to torque.
Yeah, I like the way Survey does it. Survey just says, you know what? Why don't we just skip, back in chapter 2, he says, let's just learn how to add and subtract vectors, because doing cross products is kind of hard, and you don't really need it till chapter 10. And so if we learn it in chapter 2, that's not going to help you. So let's just learn it in chapter 10. So it doesn't have its own chapter or anything. So that's kind of the bummer thing, but I like how he just kind of holds off. But anyways, that being said, all of you have been exposed and used cross products at when you did rotation, and you're doing it now because we're doing torques. Okay. So to review it, we kind of do this. We say, okay, let's call vector C the cross products of A and B. So if you have like this vector pointing in this direction, A, and another vector B, so that there's an angle between A and B, vector C will be perpendicular to those two. So that means vector C would be either coming up out of the paper or going into the paper. And we have this little right-hand rule trick to kind of distinguish those two. And here's how you do it. You take your right hand and you make it so your fingers are straight first. And you take the fingers of your right hand and you put it in the direction of the vector that's listed first, which in my case is A, but also in this problem, happen to be A.
And that's that A is the I think it's a perpendicular line to the actual rectangle on that top right image there.
Yes, yes, yes. So that's another important thing, that the definition of an area vector is perpendicular to the plane.
Yeah.
So if this was the plane, I'm trying to draw an area vector that starts at the plane and goes into my drawing. And so that's going kind of in the drawing. If it was three-dimensional and this was the rectangle and I was holding it up like this, the area vector would be going
Into the page, yeah.
into the page like that, like that.
Okay, and then you cross it with the magnetic, with the B.
Yeah,
Yeah, okay, I see.
right, right. And that's the part where you got to get kind of tricky with your wrist. You got to leave your fingers still pointing in the direction of A, but then you kind of want to rotate so that you can close your fingers. So in my drawing, if this was B, I would close it. Back to the problem at hand, I had to do something like this. I first put my right hand in the direction of A, but then realized where I'm positioned now, I close my fingers to a direction that is not towards B. So I have to spin it around. Now I can close it towards B. And
Okay,
so my
and
thumb is in the negative Y.
The negative J hat, I see. Okay.
Yeah, and then that's where the negative J hat comes. It's a symbol for the negative Y direction.
Mm-hmm. All right, thank you.
Okay. Good. All right, let's go. I'll go back to the chat. 21 question. All right. Ryland? Am I saying it right? Yeah.
I think
Ryland?
he turns off the volume on his computer, so I would just send a text chat.
Oh, okay. Looks like he's looking up here now, but Ryland, are you there? Oh, he's talking.
Cool. Sorry.
Oh, he's muted.
Microphone's off.
Can you hear me now?
I can hear you now.
Cool.
Right.
I had another question for you. Strangely,
Great.
another one that's combining sort of similar to the one we did before, that's combining the sort of centripetal motion with conservation of energy laws.
Should I let you share the screen so I can see it?
Yeah, that's probably what to do. Is it?
Yeah, I don't think I've given that permission yet to start. We did at one point.
Thank you, Dr. Young. I might see you next session, but I have to go for now. I appreciate your help.
You bet. We're getting into some tricky stuff, I know. And so are the 121 people. And so are the 102 people. I haven't seen any 102 people today yet, but there's some tricky stuff there too.
Thank you very much. I got to go. I'll see you later.
Okay. Okay, so I think I got to stop sharing and give you permission. Oops. All participants, one at a time. Okay, I think that'll work. Should be good.
Yep.
All right, let's take a look at this problem.
Cool. So let's see. This is sliding down a spherical hill.
Oh, yeah, I see what you're saying. Energy. Yeah, this one just, as you said, smells like energy and centripetal, just like the last one we did. Okay, let me put a time here. What is this? 2:03. Oh, is there a break time? Well, we better do this. We better do it If you got the strength, I
if
got
you
it.
need a break, I know you've probably been doing this forever, so if you need a break, I'm happy to come back and do this at the beginning of the next session.
No, I'd rather pound it out if you're good with it.
Yeah, I'm happy to.
All right. Good. All right. So this is a circular one down a hill. Let me just read it here. A toy with a mass of 1.25 kilogram slides from rest. Okay, that's going to be important. Initial speed is 0. Slides from rest on the top of a frictionless sphere. Okay, that's important. Remember, we talked about the heat. I'm going to just write down here in my notes. Heat equals to 0. At a point on the sphere which makes an angle of 30.2 degrees, I'll draw a rough picture so I know what angle they're talking about, 31.2 degrees, away from the vertical, even says. The normal force on this, the normal force of the sphere on the toy is, oh, okay. So normal force and sphere. Oh, and I think we're supposed to find that. That's a question, right?
Yeah.
Okay. Then when the toy reaches an angle of theta max away from the vertical, it loses contact. We're going to get to that same discussion we had in the last section, that would be when the normal force is 0.
Mm-hmm.
And I'll remind you of that. When loses contact with the sphere. Hint, use conservation of energy and centripetal acceleration. The surface of the sphere at which point acts like a ramp tilted at an angle of theta. The radius of the sphere should cancel out. Oh, yeah, okay, that's good he said that, because I was just thinking myself that radius is going to come into play, but it also might cancel out. And so he's kind of helped us there. Okay, so I drew a rough picture. Let me...
Well, do you still need this? Do you want to take the screen back so I can...
Oh, I don't.
Cool.
If I have anything, I'll ask you about it.
Cool.
Yeah, let me come back to the camera. Come on. A little slow. There we go. Nice. All right, so this is kind of my quick hand sketch while I was reading it here.
Mm-hmm.
And so let's kind of put the little toy into my diagram. And the first part of it was to find this normal force.
Mm-hmm.
And as the hint gave, and you pointed out, and we talked about last time, that we probably need to do both conservation of energy from the current material you're learning, as well as centripetal accelerations and centripetal forces from the past chapter. I'll start with the energy, only because that's what we did last time, and we did last time only because that was the new material. Okay?
Mm-hmm.
But like any of these conservation of energies, I'll say it has some initial gravitational potential energy. It has some initial kinetic energy. And in fact, just like the last problem, I won't bother to put the energy for a spring, the 1/2 kx squared, not really even kind of relevant for this. The other side of the equation would be the final energies. And just to remind you, we had this discussion about heat. I like to put it on this side, but you could just as well put it as a subtraction from the initial energy on the other side. Either way, for this problem, we can cross it out because there is no friction.
Mm-hmm.
So we don't have any heat, just like we don't have a spring. So we only have these two energies to mess with. And in fact, I'll even go one more. they said it was starting with an initial speed of 0, or they said
Yeah.
from rest, and they're going to make us figure out that that means 0. Now, here would be my question for you, and I want to point out there's no right or wrong answer, but when you go to calculate these energies, somewhere you have to pick your grid.
Mhm.
Somewhere you have to say, where do you want the Y to be 0 so you can calculate the potential energy?
Yeah, so to me, the logical spot seemed the origin,
The center of the circle?
center of the circle, so that I could have the radius be my y initial.
I agree. I think anything else is going to make it hard. So that would be my choice too. I
Okay,
just wanted to overemphasize that
yeah.
you can pick it anywhere you want. So don't, if you look ahead to see what might be the easiest, but sometimes you get that right and sometimes you don't. Just know that you can start over, or you know that it can still work out, just be harder wherever you pick it.
Okay.
All right. So I think that's a great pick, and so I'm going to go with it too. And so what that would mean is this first term for the gravitational potential energy would be mg, and its initial height would be r.
Mm-hmm.
Okay. Now, on the other side of the equation, we would have an mg, and as you can see, the picture, the y value is a little bit less.
Mm-hmm.
And it would be r times cosine of 31.2 degrees. And should I run through the trig,
So
or do you?
the trig here is something that was hanging me up because I was confused. I guess the trig is just, no, it's the cosine, it's the adjacent to the angle. Okay, I get it. I don't know why I was tripping up over that when I was thinking about it by myself, but that makes sense. The cosine is the adjacent. I went a more complicated route and said that the r there was sine of 90 minus 31.2, but it's more complicated.
Well, yeah, and then you can do the difference of two angles, and you end up with cosine of 31.
I just, for some reason, wanted to go from the x-axis up to the point, but I didn't think to just do what you did. So, yeah, that makes sense.
Yeah.
Okay, cool. I see it.
Okay. And then, like I said, then if you put sine of 90 minus 31, then you would have done the trig identity for the sine between two different angles, and you would have came up with the same thing in 2 steps.
Okay, cool.
So it would have been a little harder, but not unreasonable.
Okay, cool.
Okay, now the other term, this 1/2 m, the final squared, I really can't do anything with yet. I should emphasize that, yet. And I'm just going to leave this alone for a second.
Okay.
And do the other half of it that you talked about, as well as, I'll say the author, but I think the author is your instructor, Doug, right?
Yeah, Doug.
Who, and so his hint he gave you was look also at the centripetal force. So now I'm going to go to a free body diagram and kind of put this box here and say, okay, maybe I'll draw just to remind myself that it is on the edge of a sphere. So I'll kind of draw a quarter of the sphere. And so it kind of looks like maybe this is the center. Okay. But the important part of this is that the two forces would be, maybe I'll darker blue so the forces stand out. The force pulling it straight down is mg. And the force perpendicular to the surface is the normal force. And that's really kind of the key here. Now, I'll ask you again, what grid do you want?
So I guess it would be good to, like he said in the hint, we can treat it as if it's on a ramp at any particular point. And so then I would draw a grid that's sort of like the x direction points parallel to the direction of the box at yeah, like you drew at that moment.
Yeah. Yeah, and that's a good hint because it works out a lot better that way. But I'll say it again, either one would work. But I don't know if it was you, but somebody else I was hoping in 121, back when we were doing these circular motions, I would always put my grid so that one axis, either the X or the Y, doesn't matter, is along the radius and the other one is tangential. Because the one along the radius would be the acceleration of v squared over r, and the one perpendicular to that, which in this case, the x-axis, would be how the speed is changing.
Okay.
And anything other than that just gets real hard. So, okay, so taking that hint and, you know, and I guess I'm repeating Doug's hint that, yeah, that's always a good idea in circular motion. And it's because of the v squared over r, it's towards the center of the circle. When I go to add up the forces in the y direction, the easiest one to deal with is the normal.
Mm-hmm.
Here, if you kind of do a little geometry and realize that gravity is straight down, which is a vertical line, and then this y-axis over here is a vertical line. These two are alternate interior angles.
Mm-hmm.
So it'd be 31.2. So the component of gravity would be mg cosine of 31.2. And of course, it would be in the negative direction. So that's the part where I would say, okay, add up all the forces. And there's only two forces. The normal force is one of them, and a component of gravity is the other one. And that's the same component we got for a ramp. So I'm sure that's why he put the hint there that, look, for a ramp, we got mg cosine of the angle. So for this one, you're going to get mg cosine.
Okay.
And I'm hoping that's fairly easy to see. So I don't know if the hint is necessary, but it doesn't hurt.
Yeah.
Okay, so then remember, you add up all the forces and you set that equal to MA. Okay, well, in this case,
MA is going to be v squared over r.
that's its magnitude, yes. What direction?
It's negative.
Yeah, it's towards the center of the circle. I like to say it that way. It's always towards the center of the circle.
Yeah.
Our grid, we chose that to be negative.
Gotcha.
And some people will always call the positive axis inward towards the center of the circle for just that reason. So they always have to have a positive there. I usually just let the student decide, okay, which way do you want to call positive?
Mm-hmm.
And then in your case, you said outward is positive. Okay, good. And that just means that the acceleration is inward, which is negative. Okay.
So if I had set my grid up where essentially up, I guess I'm a little confused there. Because didn't we say that the center of the circle was Y, or are we moving on to, are we still working with that? Was it
Oh,
zero?
so I'm working with Y only, yeah. And
Yeah.
so this is the center of the circle. That's what I'm saying. The acceleration in the Y direction is V squared over R.
Yeah. So would we have been able to, I don't know how, if I made the center of my circle 0, how I could have possibly had up, like, out be the positive direction. Does that make sense? Maybe I'm confused.
You mean if I put the grid right there at the center of the circle?
Yeah.
Are you still going to tilt it?
Okay.
So,
I see what you mean. Okay.
but that your centripetal would still be this way. You could call your origin there, but remember when you talk about the direction of vectors, the position of the origin is irrelevant.
Right.
So if you wanted to draw it here, that's fine, but you're still thinking about the forces at this point where the object is, and so it would be downward in that direction. So
Okay.
you're still going to have a negative direction, even.
Gotcha. Okay, I see what you're talking about. Cool.
Okay. But now I think you can see how what we did earlier, and I'll put it back into the screenshot here, has a V squared in it, and this has a V squared in it.
Mm-hmm.
So what I'm going to do then is to solve this for
V squared.
V squared. So I'm going to, let's see, what's the best way to do it? Maybe I'll put an R and an M over here first. An R over an M. Then I have the mg cosine 31.2. That'll be a negative V squared. Maybe then I'll just put a negative on both sides. Maybe I'll cancel an M there.
Aren't we trying to solve for n?
Well, this first one we're trying to find, yes, and the normal force, yeah.
Okay.
So I'm going to then come back up to here and rewrite.
Would I be crazy to just solve for V squared in the other equation and substitute that into my equation that already has n in it?
No, actually, I think that would be easier. Oh, I like that. Okay, let's do that. Let me cross this out.
Okay, cool.
Yeah, I think yours is going to, yeah, that direction will probably less math. Okay. So let me cross this out. Okay, so let's take what you had. There's the n, there's the minus the mg cosine 31.2 equals. Let me just move the minus out in front. There's the m, there's the r. And as you said, back here, it would be easier to solve this one for the v. In fact, there's an m in every term, so I will first cancel those off. You made note of that last session. And then I'll put the 2 in front there, and canceled off there. So this would be a 2GR, and then minus 2GR cosine 31.2.
Mm-hmm.
And then I think this was part of the hint that the R is going to cancel off. Good. And so is the M. And so we get N minus G cosine 31.2. Over here, we get a minus 2G. This becomes then a plus 2G cosine.
How did you cancel the M in that?
There's
Because
Oh.
I don't see an M on the N
Yeah.
chart.
I can't. Sorry. Yep. Yeah, you're right. It is time for me to need a break. I'm getting thirsty.
I hear ya.
Okay.
My brain starts to go nuts at this stuff after a while too.
Yeah. Okay. So sorry about that one.
That's okay.
All right. But the R is canceled, right? Yeah,
Yeah.
that was correct. And so let me just leave that alone. N minus G cosine 31.2. M, shoot, still there. But it's this side of the equation that I have the minus M. And then I canceled the R's, so that would be a 2G if I factor it out. 2G, there's a 2G here. And then the cosine of 31.2. And so this would be an N. And if I put this together, it's minus 2mg. And it's a plus 2mg cosine 31.2. And bringing this over is plus another mg cosine 31.2. So we did that right. There's 3 positive ones. And 2 negative ones. Yeah.
That algebra is hard on the brain right now. MG.
Yeah. Yeah, I'm just looking back over my algebra. I think I got that right. Maybe I should start with this.
I think you did too. So.
'Cause I had this negative m over r and then this v squared. So that's a 2gr minus 2gr. Yeah, now that cancels. And so you're going to be left with a 2mg here. And then this one over makes a third. So 3 mg's. And then over here is 2 of them. Well, I'll tell you what. I'm going to, so we have a little bit of a break. I'll be back in a half hour. But let me just point out, so the other half of this question, though, was, let's see, so the first one is get the normal force. So assuming that we didn't make any mistakes, plug this in and put it in there, and that should be the correct normal value. But now when the question asks, when does it leave? we could do something like this. We can, so I'll go part B, say it's going to leave when the force gets low enough that the normal force becomes 0. That was kind of our discussion with the roller coaster one.
Mm-hmm.
And the only thing I would change then in the whole process is instead of having a known angle of 31.2, I would just write it as theta.
Gotcha. Okay, cool.
So then you would have, oh, and actually then the math comes out real straightforward.
Yeah.
The M and G cancel off. The 2 you can move to the other side, make it positive, then divide by the 3, and then have cosine of theta. And so the inverse cosine of 2/3 would be the angle. Which, and I'm curious what that is. Inverse cosine of 2/3, about 48 degrees.
M and G cancel off.
Well, sorry, I shouldn't say canceled. I can factor them out, and then when I divide, 0 divided by anything is still 0.
But oh, right. Okay, cool. I see what's going on there. Yep.
Yeah, so
Cool.
I didn't really, cancel was the wrong word, but I divided by, and 0 divided by mg is still 0. So I go.
Yep. Awesome. Thank you for delaying your break for me and working that one out.
That's a fun one.
Cool.
But yeah, I'm gonna go.
Yeah.
You know,
I'll see you in a bit, I'm sure.
sadly, my window faces the west, so it's this afternoon that always gets hot on me. All right. See you in a bit.
Yeah. -2.